All right, ladies and gentlemen, welcome to 7.3, Solving Trigonometric Equations. So we're going to be using some algebra, which some of you guys I'm sure are very happy about, and obviously using some trigonometry as well. We will be using some of our identities, a couple of the ones we've been using already, mainly the Pythagorean identities. So make sure you know that one as we move forward. So we're going to start off with the good old days. We're solving for x, and we're going to look at this as being x plus the square root of 2 is equal to the negative x, or the opposite of x. And I'm pretty sure every one of you could probably still solve this. If you added x to both sides, you would get 2x plus the square root of 2 is equal to 0. You'd say 2x because you would subtract the square root of 2, and you'd get 2x is equal to negative root 2, and therefore x is equal to negative root 2 over 2. And you could solve that and you could simplify that, and you would know that those two things, that x is the right answer. Okay, so remember, you might remember I use this stuff to kind of compare to trigonometry. So we'll give a few minutes here. We've got a couple examples of the good old days. Here's 3x minus 1 equals 0. I'm hopeful that every one of you guys could probably solve this without even thinking. If I added 1 and divide by 3, I'd say x is equal to 1/3. Super simple, nothing really complex about it. This one here, it might take you a couple seconds to actually figure out how to do it. And yes, you could use the quadratic formula, but this one does factor to 2x and x, and those both have to be 1s, and I need a minus 1, so that means I need more negative than I have positive. And when that thing equals 0, therefore, this is the part you guys have to remember, and you guys know this, 2x plus 1 equals 0, and x minus 1 equals 0. And here, subtract 1, divide by 2, x is negative 1/2, and here x is 1. And so we've solved this equation, showing that there are two solutions, negative 1/2 and positive 1. So what we're going to do with this is basically we're going to replace these x values with trig functions like sine of x and cosine of x and tangent of x and all that sort of fun stuff. So I will mention that you'll probably want to have your circle out right now so you can see where I am getting some of these numbers here that I'm going to look at. But let's take these three equations and let's move on to new stuff. Let's move on to the trigonometry part of this. And I'm going to start with basically the exact same problem, only instead of x, I'm going to have sine of x. Now, what you need to remember is we are still solving for x. And so part of this is the algebra still works. So what we're going to do first, though, is we need to solve for the sine of x first. And after we solve for the sine of x, then we're going to solve for x. And that's where our circle comes into play. So we're going to do the same thing. We're going to add, pretending like this is a variable, we're going to add sine of x. Now, you got to remember that we are dealing with an equation now, and we're trying to solve. We're not verifying anything anymore in this section. So we're going to solve, so we can add across the equal sign. So I get 2 times the sine of x plus the square root of 2 is equal to 0. I get 2 sine of x is equal to negative root 2, which means I get sine of x is equal to negative square root of 2 over 2. Now, that's not your answer, because I need to know what is x. Well, x is some angle that when we plug it into the sine function, we get negative square root of 2 over 2. And we usually actually ask going from 0 to 2 pi. So that just means one full circle. If you go to your circle and you look for everywhere that a y value is negative root 2 over 2, And if you spend a little bit of time with the circle, that's this 45-degree angle there, and this 45-degree angle there. So that is 5 pi fourths and 7 pi fourths. And so notice that we get two answers here, where on the algebra side of this question, we only got the one answer of negative root 2 over 2. But you got to remember that we're looking for x. And now we've done this type of problem before, where what sine of what angle gives me negative root 2 over 2. So we're going to use that we already know how to do and combine it with the algebra that, again, we already know how to do. So we need to be able to merge them together using algebra, using our trigonometry to do so. So let's look at the next example for this, this type of new stuff. We get, just like I had earlier, where I had 3x minus 1 equals 0. So here I have 3 tangent squared minus 1 equals 0. So I'm going to add 1 and divide by 3. This means that tangent squared is equal to 1/3. Oh, I forgot to put square on the last problem, but that's okay. Add 1, divide by 3, get 1/3. Then I'm going to square root both sides. So I'm going to say that tangent of x is equal to, if I do a little scratch work up here, the square root of 1/3 is the square root of 1 divided by the square root of 3 multiplied by root 3 over root 3 to simplify. And I get the square root of 3 over 3. But you got to remember that when you square root something, both sides of an equal sign, you get positive root 3 over 3. And you get tangent of x is equal to negative square root of 3 over 3. So then the question is, where is that? What thing is that? You got to remember that tangent is the y value over the x value. So you need to go to your circle. You need to find something where it is root 3 over 2 divided by, oh, not root 3 over 2. Sorry, you need to look for 1/2 divided by root 3 over 2. And if you get that, that's 30 degrees. And tangent is positive in quadrants 1 and 3. So you go around your circle and you look for, you're basically looking for this on your circle. You're looking for a positive, root 3, root 3 over 2, comma 1/2. And you're looking for a negative root 3 over 2, comma negative 1/2. You're looking for y over x there. And those coordinates happen at 30 degrees. So pi sixths. It also happens in quadrant 3, which is 7 pi sixths. And the negative version of that happens at the 30-degree angles in quadrants 2 and 4. So we also get 5 pi sixths and 11 pi sixths. So look at there, we got 4 answers for one question, and one very basic question there. But we were basically looking for this on our unit circle, looking for the y coordinate of 1/2 divided by the x coordinate of root 3 over 2. All right, so again, remember we just did some algebra and then solved for those x values. Last one on this page here is going to look like this. Again, just like that quadratic that we just did on the other page. So This looks just like a 2 something squared minus something minus 1. So it's a 2x squared minus x minus 1. It's going to factor. We've done factoring these problems before already, just in the last couple days. And we already know that this one factored like this. And just like I wrote out before, this tells me that 2 sine x plus 1 equals 0. And this tells me that sine x minus 1 equals 0. Here I can subtract 1 and divide by 2. Here I'm going to add 1. And then I go around looking for the sine, or the y-coordinate, of negative 1/2. And that occurs at 30-degree angles in quadrants 3 and 4. And those are, what are those? 7 pi sixths and 11 pi sixths. And the only place where sine of x is equal to positive 1 is at 90 degrees, which is the same as pi halves. And there you go. You get 3 answers, which you could check. You could plug them in and make sure it worked. So let's move on to a couple of things to make note of. Now, there are more examples, so don't think that we're about done here, because there's different types as well. So things to make note of. First of all, this works just like algebra for the most part. So we can deal with adding and subtracting and multiplying and dividing both sides of the equal sign. We can technically use quadratic formula. We can factor. We can, whatever you need to do, just like you would do in algebra, only it's dealing with trig. So when you get special numbers, like the examples that we just did, all of those were special numbers. Anytime you see like 1/2 or √3/2 or √2/2 or other variations of those, just use your unit circle to find the exact answers. And for the most part, you're going to be putting your answers in radian mode. However, degree mode is also fine. When you don't get special numbers, and I'll have one coming up here in a little bit, you have to use your calculator to find the inverse trig answer. So you have to actually do the trig or the sine inverse or the cosine inverse, depending on whatever example you're doing. There are chances to get no solutions. Don't think that there's always going to be an answer, because there could be none, and that's actually okay. Or maybe you got 2 answers, but only one of them really works. And that's where you got to make sure you check your answers. There are certain times when you can actually, when something's not going to work, or possibly not going to work. There's that for you. If you've been paying attention for the last few days, I'm going to throw that up there. Again, don't tell your friends. Even if they ask, be the bad guy. Tell them, I don't know. So have fun with that. Number 30 there on page 552. All right, so let's look at a couple of extra examples here. Some more interesting types of problems. What about 2 sine squared x plus 3 cosine x minus 3? Now, some of you are probably looking at this going, well, that's not much different than what we just did. However, it's extremely different of what we just did. If we thought about this as algebra, we would say this is like 2x squared plus 3y minus 3 equals 0. And there's no way to solve that problem, because now we have 2 different variables going on. However, we have a whole green sheet of trigonometric identities. And I want to be able to change cosine into sine or sine into cosine. And since cosine is linear here, I can't change it. However, I can change sine squared. I know that sine squared is the same as 1 minus cosine squared. So notice I will have to, or you will have to use some sort of identity at some point in time in this lesson. So I did that. I'm going to distribute the 2. I'm going to keep whatever else I had there. Then I'm going to combine like terms. And I'm going to say, okay, this is negative 2 cosine squared x plus 3 cosine x. Plus 2 and a minus 3 makes a minus 1 equals 0. I don't really like dealing with negative quadratics, so I'm going to multiply this entire equation by negative 1, and it's completely legal. So don't think I'm misleading you here. And this actually is a factorable quadratic. All right, if you need that next line, write it where you say that 2 cosine x minus 1 equals 0 and cosine x minus 1 is equal to 0. But I kind of like to do this straight off from these. I say this tells me that if I add 1 and divide by 2, it tells me that cosine x is equal to 1/2. And here this tells me that cosine x is equal to 1. Well, for cosine of x equal to 1/2, 1/2 is a special number. And that only happens at 60-degree angles. So at a 60-degree angle, that's actually pi thirds. And cosine is the x. So I'm looking here for positive x values of 1/2. So that's in quadrants 1 and 4. And the last one down there is going to be 5 pi over 6. And lastly here, cosine of x is equal to 1 at 0. All right, so again, remember it's just like algebra. Just got to throw some trigonometry there at the end. This is an interesting example here because it doesn't really look like you can do anything. But if you were to think of squaring both sides of the equal sign, if I squared that and I squared that, the left side, this is something that you just got to become familiar with. If there's two functions, they're both linear, what you can kind of think of is trying to square both sides. Now this one, the left side, you have to remember to FOIL. So you get cosine squared x plus cosine x plus 1 equals, this becomes sine squared. And then this problem looks exactly like the first one, or not exactly like it, but in the same style, where I have two functions, but I can change one into the other. So I'm going to change that sine squared into 1 minus cosine squared of x. And what I'm going to do here is now get everything on one side like algebra tells you to do. I'm going to add cosine squared x and I'm going to subtract 1. And I'm going to get 2 cosine squared x plus cosine x is equal to 1. That's nice because now the quadratic is equal to 0. The quadratic's much easier solved because now I can just factor out a cosine. And then I can solve both of these. I can say cosine of x is equal to 0. And I can say also that cosine of x is equal to, okay, so add 1, divide by 2. And what you'll notice here is this tells me that cosine of x is equal to pi halves and 3 pi halves for the 0. And as we just found out a minute ago, that this is going to be pi thirds and 5 pi thirds for the other ones, for the cosine equals to 1/2. Now here's the thing. If you square both sides of an equal sign, you may have created more answers than there were possible. So if you do this, you better check your answers, because I know for a fact that some of these don't work, or at least one of them doesn't work. So you go to your circle and you say, okay, cosine, or let's say we take this answer, pi halves, we plug this in. Cosine of pi halves is 0. We already figured that out. 0 plus 1 is 1. Sine of pi halves is 1. That means this one gets a check mark. It's a good one. Cosine of 3 pi halves is 0. Plus 1 is 1. Sine of 3 pi halves, however, is negative 1, which means that one doesn't work. Next one, pi thirds. Well, the cosine of pi thirds is 1/2. 1/2 plus 1 is 3/2. Sorry, just checking my work here. Sine squared minus cosine squared, cosine x. Oops. Oh, man. I messed up a little bit here. This, when you foiled this, sorry, I have to add this in here. And there's no way outside of me doing this, just to show you that I make errors as well. But you guys knew I did that. All right, so back up here, when I foiled this, I foiled it incorrectly. I hope you guys saw that I foiled it incorrectly. That makes a 2. That makes a 2, so that doesn't get there. So this one is cosine of x equals 0, and cosine of x is equal to 1. Oh, goodness. So everything in blue here needs to change. Sorry about that. I was not doing my best math there. Cosine of x equals to 1. That happens at 0, and that's the only time that happens. I was realizing when I was doing the math that pi thirds and 5 pi thirds will not work. Neither of them work. And I knew that wasn't the case in this case. All right. So make sure you foil correctly, like I chose apparently not to. Then this became a 2. I factor out the 2 as well. And I got 0. So now when I plug in 0, cosine of 0 is 1. 1 plus 1 is 1. And sine of 0 is 0. And something is not working for me either here. Man alive. Oh, my goodness. That's a plus 1. I am just out of it on this problem. Holy cow. Guys should rub your fingers at me. Okay, so this was supposed to be pi. Because cosine of x is equal to negative 1. And that happens when x is pi. Now when I plug in pi, pi will work. So my answers are supposed to be pi and pi halves. All right, so you notice I can make errors, and I know you guys will as well, but that's what I'm there for, to help you guys out and fix errors. All right, secant squared x minus 1, or sorry, secant squared x minus 2 tangent x equals to 4. So this is another one where you're going to use your identity. Noticing that secant and tangent are actually compared in our Pythagorean identity. And secant squared is equal to 1 plus tangent squared x. So I got minus 2 tangent x equals to 4. I'm going to subtract 4 to both sides. I get minus 3 equals 0. Luckily, this one is factorable. So here I get tangent of x equals to 3, add 3 there, and this tells me that tangent of x is equal to -1. Well, one of them is easy and the other one's not. Because tangent of x equals to 1 occurs at 45-degree angles. We can do that. So tangent of x equals -1. The 45-degree angles in quadrants 2 and 4. So that is, let's see, 1, 2, 3 pi fourths. And 5 pi fourths. Sorry. 5, 6, 7 pi fourths. Pay attention here. But then the other one, well, 3 is not a special number. So you're going to actually have to do tan inverse of 3. And I'm okay if you guys just leave it like this, or you can actually plug it in your calculator. If you were to plug it in your calculator, tan inverse of 3, remember there's 2 different modes. I'm in degree mode right now. So if I did tangent inverse of 3, I get 71.57 degrees. Or if I did it in radians, so you'd actually have to change your mode, I get 1.25 radians. Don't write that as 5 fourths either, because that is a rounded number. All right, what else? Last type of example here is something that happens with multiple angles. And that would be something like this. The multiple angle being this 3x here. Now this works exactly like before, so we're going to add 1 and divide by 2. Oops. Let's fix that so I don't screw this one up. Let's say, as it's supposed to be, cosine of 3x is equal to 1/2. So this is basically saying cosine of something is equal to 1/2, and we know that that something occurs at the 60-degree angle, so pi thirds, and at u equals to 5 pi thirds. Now here's how this is going to work. You didn't need to do this step. I can say it's 3x is equal to pi thirds. And I can say 3x is equal to 5 pi thirds. But here's the thing. You can't just divide by 3 and only get those 2 answers. Here's what happens. Things happen on the unit circle itself where this can occur. So we need to think about the period. So we need to add, so I'm going to write this up here. Add period of the function. So if I added 2 pi, or 2n pi, let's call it 2n pi, some multiple of 2 pi. We're adding some multiple of the period. Then I can divide by 3. So I get pi over 9 plus 2n pi over 3. Bear with me here. Here I get x is equal to 5 pi over 9 plus 2 pi n over 3. I need to convert to the same denominator here so I can do the math involved. So I get x is equal to pi over 9 plus 6n pi over 9. And this one, same idea. I get 5 pi over 9 plus 6 n pi over 9. Now here's what you need to do in order to figure out what x actually is. It's obviously pi ninths. So if n equals 0, you get pi ninths. Now here's what you do. You just add 6 over 9. So here's a 1 over 9. So you add 6 over 9 until you get something bigger than 2 pi. So if I added 6 over 9, this becomes 7 pi over 9. If I added 6 pi again, or 6 over 9, I would get 13 pi over 9. If I added 6 again, I'd get 19. But 19 over 9 is bigger than 2. So that's the first 3 answers. Then you have to do the same thing for the second answer. So when n equals 0, I get 5 pi ninths. When I add 6, I get 11 pi over 9. And when I add 6 again, I get 17 pi over 9. If I add 6 again, I've gone too far. So notice what started off as a very simple problem didn't get extremely hard, but it started off with only 2 answers, but ended with 6. All right, so you have to think about adding the period of the function, some multiple of it, and you just keep adding that thing until you reach something bigger than 2 pi. So you got to remember that sine, cosine, secant, and cosecant also or all have periods of 2 pi, where tangent and cotangent have periods of pi. So here's your assignment for you guys. What is that? 25 problems. Got a couple days in class to work on them. Hope some of you guys get started today so you guys can ask me questions, good questions tomorrow. I will see you guys later.